Hi, welcome to my video all about the 12 volt battery. It's quite often a problem that the 12 volt battery can go flat, and in particular on the Fisker Ocean that has a hard time because it's got a solar panel, and when the solar panel engages it drains the 12 volts at the same time. So I've spent a long time doing a lot of measurements and a lot of changes on this car, but all my thoughts and measurements down in a document that you'll see in the video description section. But if we have a quick look at some of the changes. So say under here, we've got a unit here that charges the 12 volt battery from the solar panel. And you can see that the unit is operating at the moment, even though we haven't got direct sunlight on the roof. And I've got this lithium ion poly battery, which does most of the hard work, the grunt work of the car charging and discharging. Also got this loose bit of wiring is the Bluetooth monitor that's made easily removable by these crocodile clips on the battery. I've also got a shunt monitor which measures both current and voltage going into and out of the 12 volt battery, and you'll see some of the measurements from that in the document that as I say is in the video description section. So why did I power the 12 volt battery from the solar panel? Well, obviously is to keep it topped up, but also when the solar starts to produce some electricity, when the sun is on it, it engages charging the high voltage battery using an inbuilt inverter, and at the same time, to power both the electronic systems and probably a water pump, it's draining the 12 volt battery. So if we can charge the 12 volt directly at the same time, then it won't flatten the 12 volt, and there won't be a need for the high voltage to regularly turn on and charge the 12 volt, which the standard car has to do every so often. It has to recharge the 12 volt when the voltage gets down to about 12.5, 12.6 volts or something. And the efficiency of doing that, coming off and on all the time, negates any gain you get from the solar panel, it would seem. So how do we tap into the wiring to get to the solar panel connections? We'll see next. So according to this wiring diagram, the colours of the wires coming out of the solar interface panel going to the photovoltaic interface unit are purple and red, which you can get to here, that one, and also yellow and purple, which is that one. And as you can see, I split into each one, and even when it's dull you're getting just over 12 volts. So yeah, it's bright but not sunshine, and I'm guessing you get more current as well as fraction more voltage once the sun starts shining on it. And what I'm going to do now is snip off the positive supply, which will disable the solar, cut through this one. It's only 12 volts, so don't worry about getting shocks from it. And I'm going to use these pretty old snippers, so I'm going to snip through that, and then we'll see what the 12 volt battery does after that. So that's it, snipped off. What's coming out of the solar interface unit, in other words the solar panels, is now 15 volts because we have snipped it off, and therefore it's not consuming any current. Very small residual voltage of 40 millivolts left on those wires that go off to the rest of the system. So yeah, let's have a look at the battery drain now. I'm going to lock the car again, and we'll monitor what happens. Once the car is locked, then the current consumption on the battery drops down to 0.2 of an amp, which is reasonably acceptable. But it took a few minutes to get there, and for a little while it was taking something like 13 amps, probably more without the resistance of the meter and the cabling in series, which again is quite a lot, and you can see that on the discharge graph of the 12 volt battery. So let's again see the effect of the solar panels by reconnecting that solar panel wiring and waiting a little while for it to go to its static state. So connecting the solar panel via my meter shows it's delivering about 4 amps. Again, it might be limited by the meter itself, and it was around about 12 volts. amperage is going up 7.8 as the sun is just starting to come out behind the clouds. So yeah, we're over 12 amps now, which is over the limit of the meter. So it gives you a rough indication of the sort of current that you get, 15-16 amps. With the solar panel reconnected, so it's presumably charging the high voltage battery, but it's draining the 12 voltage battery by 0.9 amps, which is why you see that discharge curve on the battery monitoring device. So to stop it excessively discharging your battery, making your battery last longer, then what we need to do is directly charge the 12 volt battery from the solar panels, as well as it charging the high voltage battery, which we can do via one of these battery charging modules. You can get either isolated or non-isolated, but since the solar panel earth point is very close to chassis earth, within about 40 millivolts or so, you could probably get away with a non-isolated version. Or if you really want to play safe and don't want to risk mixing the 12 volts to the solar supply, you can get an isolated charger. And there's a lot on the market, as you can see on eBay or Amazon. So you can get the smallest capacity around, because we only need the charging device to supply around an amp just to top up the 12 volt battery and stop it from draining. And I think the minimum size one you can get is a 9 amp supply. Just to check what the solar panel is doing in terms of the percentage of its capacity. With the current amount of sun on the roof, where you're getting, what was it, 15-16 amps, then the capacity is at 84%. So we could probably do a quick calculation to work out the maximum corresponding to 100%. So currently it's being charged up to 80%, and it's on 348 miles because this is version 2.1 software. And let's see if the solar panel actually charges up the high voltage battery, gives us more range for the small amount of time that the sun is on the roof. So a very small test, a few hours of the sun hitting the solar panel. At times it must have been generating about 200 watts or something. But we're on exactly the same mileage, so to make any difference, at least less than 1 mile difference to the high voltage battery. And I've got it set to charge to 100%. It's currently at 80. So I suspect, and we can test this later, that having a solar panel producing small amounts of electricity is actually doing more harm than good, because it's draining the 12 volt battery to keep the systems running, but not really providing enough power back into either the high voltage or the 12 volt to compensate for the fact that it's draining the 12 volt to keep the systems running. So probably you would get less fan power drain if we disconnected the solar panel completely, which we can verify, of course. And to get cables in between the engine bay and where our cables go to the solar panel, you can see right in there, let's get a little bit closer, in there you've got these puncturable little metal discs that are sealed onto the bodywork. Just push with whatever sort of rod you've got, one of these electrician's rods that I've got, pushed it through, and at roughly that sort of angle you will see it come out just at the spots where we want it, which is here. So that's a temporary switch I've got in for the solar panels. I'm going to move that into a proper position, but that's just where we want the cables coming through. So then I'll tape some cables to this rod and hopefully pull it back through, and the cables will follow with it. And that saves me having to take all of this plastic off, this cover and everything, which probably will be possible because, like the other side, there's a few screws underneath, and I suspect the whole thing will come off. This side panel will also just pull off, as will this as well, if you ever need to do that. Of course, I've got to take this back off again in order to get to those cables that are under there again. And then to get the cables through and to make them safe, first of all, to make them safe, put them in a bit of conduit, so you've got double insulation on the wires that we need to get through. And then I've taped them onto the rod, and I'm rather hoping I can push and pull that whole arrangement through that hole in the bulkhead. And so 2 of these cables, got to be capable of taking 20 amps at least. So this is 3.3 square millimeter cable, 2 lots of it, which is it's actually speaker cable, and that's capable of taking easily that current, while being very flexible because it's quite fine multi-stranded copper cable. Use it whatever you've got handy. This just happened to be what I've got handy, and because it's low voltage, don't have to worry too much about specification of it. It's only 12 volts. Worry more about the current, so make sure it's good cross-sectional area, and you can look up the current capacity of whatever cross-section area you've got on the internet. The other cable I run in that conduit is one for monitoring the voltage directly coming out of the solar panel, because this shunt monitor I'm going to put on will monitor the battery voltage, the battery current going in and out, and also as a secondary input for measuring another battery. But in this case I'm going to connect that to the solar panel, so it'll be interesting to see what the solar panel is doing over time as well. Hopefully we can pull that through. And with a bit of pushing with a screwdriver as well, and a bit of pulling from this side, that's the whole arrangement of push rod, tape and the 3 cables through the bulkhead in just the right position. So I've got to build up a little box area, and we're going to have a couple of switches on here for controlling the solar or the battery charging, and that's the cables wrapped in the conduit going through the hole in the bulkhead. I'll also get my finger down there and spread a bit of silicone seal around the hole, just in case water gets from this engine side into the cabin. I think I'll add a little bit more conduit onto the cable as well, and mount this smart shunt over here. So for wiring onto the solar panel wires, these are the wires again. Red and purple is the negative side of the solar panel output. Purple and yellow is the positive side. So at the moment I've got a switch connecting between where the original positive from the solar panel came from and where it connects off to go to charge the high voltage battery. So you can switch that in and out, so the solar panel can charge the HV or not. I'm going to connect up the negative side, which is going to go to my battery charger inverter module. I'll just show you that, which is this Victron Energy. I've gone for an isolated DC converter. You can get this for about 50 or 60 pounds. What's that, about $70 or something. Takes in 12 volts, outputs 12 volts. Actually, the output voltage is adjustable via that little pot where my thumb is. And pretty obvious, these are the inputs, these are the outputs. Electrically isolated, which is probably a good sort of idea and good extra bit of safety. I think you probably could get away with just having a diode, low voltage dropout diode from the positive going to connect to the battery. That's the diode, stops the current flowing from the battery back into charging the high voltage battery, which would soon flatten your 12 volt battery. This completely isolates it. Although the negative side of the solar panel connection is very close to the chassis earth potential, it's about 40 millivolts off, and to stop any earth loop currents, basically currents going where you don't want them to do, then having it completely isolated avoids that. So these blue wires are going to be the positive and negative from the solar panel. Will go into this unit. The output will go across our 12 volt battery, and as you can see here, the output is adjustable 10 to 15 volts. So even, for instance, if you had an 8 or 9 volts input for a very low amount of sun on your solar panel, then you could still charge your battery up to 13 or 14 volts probably. Whereas if you just had a diode, then the solar panel would have to be above 13 volts or so in order to effectively charge your 12 volt battery. But I'm sure it is probably possible. If you don't want to spend 50 or 60 pounds on one of these, then probably you could do that. But do your own investigations and satisfy yourself. Don't come blaming me for that recommendation, because it's on your own head. And similarly with anything I do here, take your own responsibility for doing it. But I personally think on my car this is going to be perfectly safe. And on safety, just make sure you keep these two cables perfectly far apart. A little bit too close for comfort here already. Going to insulate this one up. Don't need to connect to that again. Do need to connect to the solar panel output to switch it onto this other wire, which will go into charging the 12 volt battery directly via that converter that we just saw. So we'll have a switch for high voltage charging from the solar and a switch for charging 12 volt from the solar. So soldering is the best way of making these wired connections. It ends up more mechanically and electrically stronger connection, and it's always a good idea to have it mechanically attached before you start soldering. So I've stripped off the insulation from both cables, wrapped one around the other, and then I'm going to solder on top. So it's quite a thick cable, it dissipates heat very, very quickly. So I'm going to max out the temperature setting on the soldering iron that I've got. Try and get it really hot. Normally about 380 or something is a reasonable temperature for soldering. But if I start off at high temperature, then I've got a better chance of making the heat last longer. This is leaded solder, which has a lower melting point than some of the lead-free solder. So again, easier to solder on large bits of copper like this. So yeah, let's see how we got on. When you solder, again, I say don't be afraid of soldering, it's not too difficult. You want to aim to bring the solder and the soldering iron together at the same time, at the same point, onto the surface that you want to solder. So something along these lines, and ideally when the copper gets hot enough, which might be difficult on this one because of the thickness of the copper, but ideally we want to press the soldering iron on the copper rather than the iron as long as it is melting. This is not going too badly actually because the iron is so hot, but very quickly the heat will be taken away from the working surface. It will be conducted down the wires, so probably don't want to take too long doing it because the rest of the cable will get very hot and start melting the insulation. But give it a blow, make sure it's still make sure it's not molten, and yeah, just check that the solder has melted into and around the copper, which it does seem to have. So that is good enough for a connection, and then we'll give it some liberal coating of insulation tape around it. Try and go over it a couple of times so you've got several layers of insulation. That is good, and actually that's less critical because that's a negative side anyhow, which is pretty similar to chassis earth, but yeah, might as well do a good job of it. Right, now we've got to get exposure to the positive side of the solar panel output, so I'll just remove this bit of temporary insulation that I put on there. Right, and then I need to have another wire from this and the grey wire that I cut the fuse off. I need to reattach the fuse. I'm going to connect that to this solar panel output so that we can monitor the solar voltage directly on our Bluetooth shunt monitor. So this is the switch I'm using for this application, rated 20 amps at 125 volts AC. So that's each of these contacts, and I'm going to double them up, so go across, connect across this way. That would rate it at 40 amps at 125 volts, and of course it's only 12 volts or maybe 15, 16 maximum. So the current rating is going to be even more than that, so more than enough spare capacity for the roughly or so 20 amps that might flow out of the solar panel. It's important to get a good current rating of switch. You don't want it getting hot and possibly melting something. And for the best connection, I'm going to take these screws off, solder directly onto these tabs as well for best electrical connection and best security. So before you make any of these connections to these blue wires, make sure the other end of the wire in the engine bay, they're not touching anything and not touching each other. So just to go over the wiring again, solar panel positive output, which is this bottom blue wire, goes around onto the middle part of the switch on this side, and also goes across, even though you can't see it because it's insulated, goes to the middle part of the switch on this side. Then the one side of the switch, so even though this switch is a double throw, double way switch, don't worry about that. Just one side of the switch will be activated, in this case when you push it down into the on position. And that, for this switch, goes off, we follow the cable around, goes back to the original wire that goes off to charge the high voltage battery. So that's enabling the original connection. our new switch, which is this one, which has the exposed wiring. That's all going to be heavily insulated like the other one in a minute. Goes off, the output of that switch goes off and drives one of the new blue cables. So that's going to be our positive feed into that 12-volt converter module. The other side goes onto the solar panel negative connection. The grey wire, which I remade, reconnected the inline fuse that it came with, goes on to also the solar panel positive side output voltage, so we can monitor the solar panel. And then all we need to do is monitor it. I want to have the switches around here somewhere. I wanted a little black box or a bit of plastic or something. The closest I came is this bit of drain pipe, which I'm going to cut down and hopefully mount roughly in that sort of position, maybe spray it up if it looks a bit crappy. Let's see how that looks. Drill some holes and mount the switches on the front. And just to test it all before we mount it, I've got it wired up, switch is on. It's actually very dull now, the sun has nearly set, so there's no direct sunlight on the solar panel, but nonetheless the solar panel is still producing a little bit of voltage, not enough to charge the high voltage battery, I believe. Let's see what voltage it is. We have 13 volts, and I've set the output to be 13 volts as well. In fact, a minute ago there was something like 8 volts coming in and 13 volts I was able to get out of the unit. So really this unit should extend the useful time of the solar panel. So rather than just to have the solar panel contributing when the sun is shining directly on the solar panel and charging the high voltage battery, this time with the aid of this unit it should also for a much longer time, the first part of the day and the end of the day, be supplying power to charge the 12-volt battery, which saves the high voltage having to do it, so ends up contributing to the net overall energy. And now we can see on the current consumption and voltage graphs that rather than 0.8 amps being dragged out of the battery when the solar panel is operating, that can be cut to 0.2 if you turn the solar panel connection off. However, if you use these new modules and this arrangement that I've shown you in the video, then instead of taking out 0.2 of an amp, we're now charging it and a steady state at 0.2 of an amp on this graph. It started off higher, but now the battery's quite well charged. So, and as a result, because it's charging rather than discharging, the voltage of 12-volt battery stays completely constant at 13 volts that we've set to come out of our converter charger module. And here's my final switch panel installation with that cut down bit of drainage pipe, a couple of self-tapping screws screwing it into the plastic on the side there from behind the back, so it's quite sturdy. Some labels from my labelling machine on there to indicate it's a solar panel control. So the solar panel outputs, then you could use it to charge the 12-volt battery or to charge the high voltage battery. That's what those labels are indicating, and any combination of one or the other. So the original installation would have been obviously not going to the 12-volt and just to the high voltage. But if you haven't got very much power coming out of your solar panel anyhow, not huge benefit to charging the high voltage, so you could just have all of that power going to top up the 12-volt battery. It's up to you. So here's the final installation of the shunt monitor. This unit here measures the current and the voltage on both the 12-volt battery and the voltage coming out of the solar panel. And there is our converter box that starts working at 8 volts up to 16 volts to produce 13.6 volts to charge the battery, which is what I've got it set to at the moment. I did start off at a lower voltage, but after having looked it up on the internet about what float voltage you should have on a lead acid battery, decided 13.6 was the best. So it's tucked out the way from hopefully from rain falling on it from the bonnet gap, bolted onto that piece of metal cross strut, fairly secure. Lights on, showing that it's producing energy even on this quite dull rainy day. And yeah, this one has a little flashing light show that the Bluetooth is being produced. That connects over to your phone app. Lots of graphs and statistics on battery voltage and current. And so yeah, reasonably neat and works nicely. So even on a very dull rainy day, those are clouds, just been raining, still manages to charge the battery from the solar to the tune of ½ an amp, keeping it in tip-top condition. So a lot of the energy has been wasted running the water pumps. Not sure how essential that is on the fairly brief charge cycle at 14 volts the system goes through to charge the 12 volt battery from the high voltage battery. But I can see where some energy has been wasted in this fuse box. That relay, that relay, that relay, that relay, these are all hot. Oh, some of them very hot, too hot to the touch. The only ones that aren't is that one, that one, that one, and that one. These must be very inefficient relays. Could do with replacing those really. I see no reason the relay should get that hot. If it's getting hot because of the current going through the contacts, which I think is unlikely, then it's poorly rated contacts. If it's getting hot because of the current going through the coil of the relay, then basically there's not enough coil to create efficiently the magnetic field. And yeah, it's just poorly designed. There's no way at 12 volts these should get that hot. Never experienced relays getting this hot before. Also, what seems very unnecessary is why it takes that 12 amps sucked out of the battery when it turns off its charging cycle, as you can see in this graph. A few minutes after stopping that charging cycle, these relays have all cooled back down to what's going to be, I think, eventually a normal temperature. Certainly not hot to the touch anymore, so it's only during that charging cycle a lot of energy has been wasted. And you can hear the water pumps running. I don't know how many, probably quite a few if all of these relays are getting hot. And I suspect it's taking a lot more current out of the high voltage battery than is required just to charge the 12 volt battery. Just an inefficient algorithm, I think. A bit unnecessary. So the next change I did to take the grunt work of the charge and discharge cycling that the car does on the 12 volt lead acid battery was to look into burning a parallel connected lithium battery, lithium iron phosphate, which can tolerate full charge and discharge. So you can get them quite cheap now for about £30, about $40 or $50 US dollars. And they have inbuilt battery management systems to protect them from over or under charging, and similarly over and under voltage. They last a lot longer than lead acid batteries. So there's a couple of batteries that I considered as shown here, and I looked up and compared the range of operation of the battery, the voltage operation versus charge level on a lithium iron phosphate, as you can see on the left here, versus a lead acid, either an AGM lead acid or a normal flooded cheap, otherwise lead acid battery. The lead acid battery becomes fully charged at about 12.8 to 12.9 volts, whereas the lithium battery is around 13.8 to 14 and a bit volts. It's fully charged, so slightly higher operating range. And most of the time when you look up can you connect them in parallel, people will say no because of this different voltage operating range. But for me, in our application, that is exactly what we want, because we want most of the work to be done by the lithium battery. So the car will charge it up to 14 and a bit volts, which will near enough fully charge the lithium battery. And as the car is then doing some discharging, as it's operating its systems and water pump and so on, then all of the current is going to be delivered by the lithium battery, because it's going to go down from 14 all the way down to let's say about 20% charge, 12.8 volts. And at 12.8 volts, then finally the lead acid battery will start to contribute some current as well. So most of the current at the high end is going to be delivered by the lithium iron poly battery, which is exactly what we want. Now, to limit any potential problems of high current levels going between the two batteries, I'm going to put on a 0.25 ohm resistor, which with a few calculations should limit the current to about 8 amps. So this is in the document I've produced, which is in the link in the video description. A couple of high power resistors put in parallel. This is the battery that I'm going to use. As you can see, pretty cheap, £34 UK pounds. The combination of that battery means also you could use a very cheap normal flooded lead acid battery, which you can get for about £50. In comparison, the AGM battery is about 150, so you'll end up with a better solution, end up with a higher capacity, because normal flooded lead acid battery is about 50 amp hour, same as an AGM. This additional battery is 10 amp hour, so you end up with 60 amp hours in total for half the cost or so. I also looked at the charging current behaviour of these batteries, made sure that when they were fully charged it didn't take any current, which was true, so there's no additional load put on the car systems. And its inbuilt battery management should mean that it's a pretty safe solution as well. So here's the installation of the lithium iron phosphate battery, which we saw briefly earlier. And just in the corner there you can see the powerful resistors connected in parallel, 2 half-ohm resistors to make 0.25 ohm, and that goes in series with the lithium iron phosphate battery as a safety precaution. And you can see also we've got some pretty thick cables on there, and see that document for buying links that I mentioned earlier. So here we can see quite a nice overnight behaviour of the battery. So we had a little bit of car being charged there, going up to 14 volts at 1 o'clock in the afternoon. Battery was pretty full, pretty much turned off, and wasn't a lot of sunlight that particular day. A little bit around here, very dull day. So got about 13 and a bit volts. Not a lot of charging going on with the battery. A few fraction 0.3 of an amp there, but significantly when it went dark, about 4 o'clock, and the zero drain all the way overnight, nothing at all being taken out of the 12 volt battery. Any current being drawn by the system is supplied by the LFP battery. You can see the voltage gradually goes down to about 13 volts, and then we have a tiny little bit of peak charging 6:10 in the morning, and that's about it for overnight behaviour. And again, an overnight measured a few days earlier, 2 o'clock in the afternoon, bit of sunlight, voltage 3.5 volts or so, nothing being taken from the battery. Gets dark, voltage goes down a bit, 13 or so volts. Very little consumption, zero consumption from the 12 volt in fact. Voltage goes a bit low this time, down to about 12.7. Obviously starts to take current out of the lead acid battery at around that point, just sneaking into a bit of minus there, but still showing a 0.0, so not a lot. And then 8 o'clock in the morning, sun comes up, starts recharging the battery again, voltage up to 13.7 volts, and some positive currents going in the battery. And the car itself didn't do any charging of the 12 volt battery at all during that time. Now let's look at some typical performance when went on holiday for a couple of days. So around here, drove to the airport, left the car, turned everything off, and you can see how the battery typically behaves. So a couple of short charging cycles there, weren't really needed, hence they're so short. This time a little bit of solar energy was charging the battery, very little flattening of the battery for the rest of that day, nothing the next day hardly. Well, a little bit going down there, some more solar recharging, couple of bits of the car charging the battery, which wasn't really needed because it's already at nearly 13.5 volts. So the battery management system of the car, as we've seen before, not very efficient. It's doing it when it doesn't need to. And this time came back, battery the voltage on the battery 12.8 volts, still perfectly healthy, and drove back from the airport. Then obviously got recharged, plugged it in overnight, and so on. So yeah, very good performance of virtually, well, not virtually no drain, but very little drain over each day, and a negligible drop in the percentage charge of the high voltage battery. So that gives you a good idea of what. And it's another day with also some excellent results with no charge cycles from the car, tiny bits of solar in the middle of the day, as you can see. Not always this good, but this shows how good it can be. So there's often some really good voltage graphs over the day, what the car is doing, with negligible drain, as you can see there. The other tests that I've done are to look at the battery drain in terms of percentage, and also what the car is doing in terms of its range. So there's a few charts here with the original setup and a typical, probably quite good 0.6% drop in the daily battery percentage, and then with the solar panels set to charge the 12-volt battery directly. Fairly short time, 5 days that one, 8 days the other. But it's sort of indicative, especially when we look at the last graph. That's with the direct solar charging of the 12-volt battery and the extra LFP lithium battery. And over that time of 8 days, then you end up with no drop. Well, I ended up with no drop in battery percentage, and the range about the same, in fact a fraction more than when I started. These values vary a little bit, of course, as the temperature of the battery goes up and down. So some longer tests probably would be beneficial, but it's quite hard not to use the car for a week. But the results are indicative of quite nice, quite good behaviour of the overall car system. Okay, that's it. Thanks for watching. Good luck with yours. And as I've said already, this is just my story, so you take full responsibility for doing any changes that you decide to do to your car. But before we go, I'll just touch on a few strange bits of behaviour. So the other thing worth touching on is occasionally you can get spurious measurements out of your Bluetooth battery monitor. So you can see here in the first half of the screen, you get these spikes down to 9 volts, supposedly, all exactly the same level. And a bit suspicious because they go down and up so quickly. So it's suspicious it might be the monitor faulting out, maybe a cache overflowing or something. So at this point here, I disconnected the 12-volt monitor, reconnected it again, did nothing else, and as you can see, no more spikes. So it's just purely an effect coming from the Bluetooth monitor malfunctioning, so watch out for that. Hope that's useful. And just to confirm that it wasn't a real measurement going down to 9 volts, this is my shunt monitor that I've got on that measures both current and voltage. Handily is a way of double checking whether the voltage readings are correct. So this is today, see the time down the bottom there, and it was around about midday or something. I disconnected yesterday. But importantly, you can see the voltage never goes below about 13 volts or so. So those spikes down to 9 volts were nonsensical and just the monitor malfunctioning. Some interesting observations about charging behaviour. So it takes quite a lot for the car to indicate that the battery is, in this case, 98% charged, anywhere near to 100%. Seems quite unusual. A lot of the time you look at it and it's 60 or 70%. But it's got to 98% because it's been charging at a relatively slow 3 kilowatt rate overnight. So it's had a long time to charge the battery, and it's eventually the system has recognised that the 12-volt battery must be fully charged. And if we look at our Shunt Monitor Bluetooth monitor software, we can see that normally when the car is charging, the voltage on the 12-volt battery is 14 volts. So there's a long time here where you can see it was charging all overnight till about 9 o'clock in the morning. And then when driving home the next day, where we started driving, that's probably when I just got in the car and then locked it again, started driving. So a small initial jump up to somewhere like 13 volts. Then it dropped back down because it saw the battery was fully charged. Interesting behaviour. And again, that's when I plugged it back into the wall charger when I got home. So it doesn't always sit on 14 volts, has some sense to it. Unless the 12 volt needs charging, like in that scenario the day before. So yeah, different behaviour. Useful having this shunt monitor to check what it's doing. And the lowest voltage the battery ever seems to go to nowadays is about 12.7, which is good. That's finally it. Sorry it was a bit of a long one, but there's a lot of detail and a lot of video recordings I had to edit. But good luck with yours, and thanks for watching. Cheers. Bye.